Welcome to the Water Environment Research Foundation's TERI tutorial series. This module will walk you through a case study for Plant B. This plant uses a conventional activated sludge process. There are no current nutrient permit limits, but a phosphorus limit of 0.5 milligrams per liter is expected in the near future. Anaerobic digesters are used to stabilize the solids. The side streams from the thickening processes, the digesters, and the belt filter presses are not sampled and tested. This plant does experience nuisance struvite formation in the anaerobic digester complex. The plant receives mostly domestic waste. The current average daily influent flow is 130 mgd. The plant also accepts and stabilizes approximately 10,000 gallons of sludge each day from a neighboring facility. This is the overall plant schematic for Plant B. Some highlights of the plant's process are as follows. Primary sludge and sludge from a neighboring facility are both thickened on gravity belt thickeners before being fed to the anaerobic digesters for stabilization. Waste-activated sludge is thickened in centrifuges before being fed to the anaerobic digesters for stabilization. Belt presses are used to dewater the digested sludge prior to disposal at a landfill. Filtrate undergoes side stream treatment before being recycled to the head of the plant. Here's a summary of the influent, effluent, and sludge data that we have for Plant B. Since nutrient data is not available for the side stream flows, TERI will use default estimates for some of these values. Some additional information that was entered for this case study includes the importance of each of the business case evaluation criteria, the average labor rate for operations and maintenance personnel at the plant, which is $20 per hour, the local cost for ferric chloride, alum, slaked lime, magnesium chloride, and sodium hydroxide, and the biosolids disposal cost, since labor and other direct costs, parts, materials, tools, spent dealing with the negative impacts of struvite forming in the system are not tracked. TERI will estimate these costs. When you first open TERI, remember to click Enable Macros when prompted. This allows the tool to operate correctly. On the Start screen, the plant data is entered, starting at the top of the green column and working down through each green box. When the question, "Are the side stream characteristics known?" is answered no, the red box labeled "Click here to enter ANA digestion data" will appear. While entering data, please keep in mind that the Clear Data button should only be used when you want to erase all inputs in a tab. To change individual entries, just click on the cell and use the backspace button to delete that particular cell entry before entering the correct value. For plants that use anaerobic digesters but do not have side stream data available to enter, data will be entered on the ANA digestion screen, which is located at the Type 2 tab at the bottom of the screen. This is also the screen that will pop up when you click on the red button labeled "Click here to enter ANA digestion data." The data entered here can be found in the Plant Performance Data table that we looked at earlier. Enter all of the data that you have available. Leave cells for the data you do not have blank. The tool will assume some default values for critical data if nothing is entered in those fields. The business case evaluation criteria weighting is entered as shown here. These criteria weights will determine the formula used to calculate the BCE scores for each alternative. Please note that the 3 case studies shown in the TERI tutorials all use the same criteria. This helps to make it possible to compare the results and see how the different plant configurations affect the overall scores. The plant mass balance shows an approximation of the concentration of solids and nutrients at various points in the process. The results for Plant B can be accessed by clicking on the Plant Mass Balance text at the top of the screen or by clicking on the blue MB Schematic tab at the bottom of the screen. As you can see here, the mass balance produced by Terry simplifies the process somewhat to prevent the model from getting too complicated. Terry captures the estimates for the side stream with the highest phosphorus content. Based on the data entered, Terry calculates these values for the mass balance before nutrient recovery for Plant B. This slide shows a close-up of several of the boxes where the most significant changes in the balance occur. Once all of the data is entered, the expected performance of several options and the capital and O&M estimates results can be viewed by clicking on the Capital and O&M estimates results at the top of the Terry screen or by clicking on the blue tab labeled Results Struve at the bottom of the Terry screen. This is the screen with the results that will pop up. It presents a side-by-side comparison of the calculations for each of the following options: Struvite crystallizer high estimate, Struvite crystallizer low estimate, ferric chloride addition, and alum addition. The benchmark for the performance of these options is 85% removal of orthophosphorus from the side stream flow. Since there are 584 pounds per day of orthophosphorus in the side stream, 85% removal would result in 496 pounds per day of orthophosphorus being removed. Please note that some nitrogen is also recovered in a struvite recovery process. This is a calculation of the amounts of chemical that will be required for each alternative to meet the 85% removal performance goal. This is a summary of the capital investment needed to install the system, the annual operations and maintenance costs to keep the system running, and the value of the struvite that is recovered for each of the 4 alternatives. The business case evaluation, also referred to as the BCE, in the Terry is intended to help utilities take a very high-level, conceptual look at struvite recovery for their facility. Capital and O&M cost estimates must be verified. Remember, all capital cost estimates are based on 2012 US dollars. The BCE ranked scores are based upon the weights that were entered for the 13 specific business case model criteria. There may be additional criteria that should be used to assess the options. Therefore, the Terry provides a good starting point for looking at nutrient recovery options, but additional study and evaluation is needed before any fully informed decisions can be made on implementation. Terry uses several parameters in the financial portions of the BCE. The nominal discount rate is the assumed interest rate without inflation being taken into account. Therefore, the real discount rate is the interest rate adjusted for inflation. The evaluation period that the tool looks at is 20 years. For Plant B, based upon the business case criteria weighting that was entered, the struvite recovery low estimate alternative has the best total score of 75. For comparison, the baseline scenario represents the condition where plant O&M staff take the necessary operational and/or maintenance steps to minimize the effects of nuisance struvite formation. This table shows how each of the BCE criteria areas contribute to the total score for each of the alternatives. This graph compares the net present costs of each of the 4 alternatives that are being evaluated. The lines for the alum and the ferric chloride show significant increases in the net present cost each year because the systems have significant annual O&M costs with no recovered product to sell or current chemical costs that can be avoided. The net present cost of the struvite low estimate alternative and the struvite high estimate both have flat lines, which indicates that all ongoing O&M costs are covered by the value of the recovered products. This last chart shows how the total scores of the alternatives for Plant B compare to one another. The struvite recovery options have significant environmental, health, social, and economic benefits over the ferric chloride or alum feed systems.